Welcome to today's Explainer, where we're going to strip away the intimidation of raw formulas and ground the actual physics of motion right here in the real world. Have you ever wondered what exactly is happening mathematically when you slam on the brakes in your car? Or why sitting at the top of a roller coaster drop feels so different from actually plummeting down it? Well, today we're taking a really fascinating look at the rules that govern literally every single movement in our universe. Let's dive in. Here is our roadmap for today. First up, vectors, magnitude and direction. Then, forces, pushes and pulls. Third, work, forces in action. Number 4, energy, kinetic and potential. And finally, power and energy conservation. All right, let's jump straight into section 1, vectors, magnitude and direction. Now, what's really interesting here is how we separate simple values, like your mass or the time or the temperature outside, from quantities that absolutely demand a specific direction, like your velocity or your momentum. Think about it. A scalar is basically just a number. If I tell you it's 20 degrees outside or that an hour has passed, you have all the information you need, right? But vectors, they're a whole different story. They need direction. If I tell you a car is moving at 60 kilometers per hour, well, that's just a scalar speed. But if I say it's moving 60 kilometers per hour due north, boom, now we have a vector. We have velocity. And in physics, knowing where you're going is just as critical as knowing how fast you're getting there. That brings us nicely to section 2, forces, pushes, and pulls. So we have a direction, but to get things moving, we need an interaction. A force is simply an interaction, usually a push or a pull that acts on an object to change its velocity. Imagine you're just standing perfectly still. To start walking, you literally have to push against the ground. To open a door, you pull the handle. Every single change in motion requires a force. And because direction absolutely matters when you're pushing or pulling something, force is a vector. We measure it using a unit called newtons. And of course, we can't talk about forces without talking about Newton. His 3 laws of motion dictate exactly how our pushes and pulls behave in the real world. The first law basically tells us that things are lazy. Zero net force means constant velocity. An object at rest stays at rest, and an object in motion just keeps on coasting unless a net force interrupts it. Moving to the second law, this is the classic math equation. Net force equals mass times acceleration. And the third law, it's the great equalizer. Every force has an equal and opposite reaction force. If you lean against a wall, that wall is pushing back on you with the exact same amount of force. Crazy, right? Let's keep building on this in section 3, work, forces in action. So we have a force. But what happens when that force actually moves something over a distance? Well, that's work. Work is the bridge between applying a force and seeing a physical result. In everyday language, work might mean sitting at a desk answering emails. But in physics, work is strictly mechanical. It's the distance moved multiplied by the force pushing in that same direction, measured in joules. If you push against a brick wall all day and it doesn't budge an inch, you might be totally exhausted, but mathematically, you've done absolutely zero work. Let's make this concrete. Imagine dragging a 50-kilogram crate. You're pulling with a force of 100 newtons, but you're using a rope, so you're pulling upward at a 37-degree angle, not perfectly straight. Meanwhile, the rough floor is fighting back with 50 newtons of friction in the exact opposite direction. By breaking down the math to find only the force moving the crate horizontally, we calculate that dragging it 40 meters yields exactly 1,200 joules of net work. It's like a giant puzzle, and you've officially conquered friction. Now things get really interesting in section 4, energy, kinetic, and potential. The crucial takeaway here is the work-energy principle. The net work you do on an object is exactly equal to its change in kinetic energy. And kinetic energy is simply the energy of motion. If you throw a baseball, the work your arm does on that ball transforms directly into the ball's kinetic energy as it flies through the air. And look closely at the math for a second. It's 1/2 the mass times velocity squared. That squared part, that is a massive deal, as we're about to see. Let's look at a very real, potentially life-saving application of this. Imagine you're driving 60 kilometers per hour and you need to slam on the brakes. Let's say it takes you exactly 20 meters to stop completely. Now, what happens if you're going twice as fast, 120 kilometers per hour? Does your stopping distance just double to 40 meters? No way, because velocity is squared in our kinetic energy formula. Doubling your speed literally quadruples the distance it takes to stop your car. It doesn't take twice the work to stop, it takes 4 times the work. So that 20-meter stopping distance balloons out to 80 meters. Understanding this math is quite literally the difference between a safe stop and a severe collision. But an object doesn't even have to be moving to have energy. It can possess potential energy just by virtue of its position. Think of a massive 1,000 kilogram roller coaster car clinking its way up to the very peak of the track. It's barely moving up there, but because gravity is just waiting to pull it down, it is absolutely brimming with gravitational potential energy. It's stored energy, ready to be unleashed. This brings us to a really beautiful concept, the law of conservation of mechanical energy. Notice the equation, E equals K plus U. The total mechanical energy in a system is just kinetic energy plus potential energy. They simply trade places, while the total amount stays perfectly constant. As long as we ignore outside forces like air resistance, the energy doesn't vanish, it just transforms. As our roller coaster drops, it loses height, so it loses potential energy. But it gains speed, meaning all that potential energy is converting seamlessly into kinetic energy. When we apply this to the coaster, the math is almost magical. Say we start from rest at the top of a 40-meter hill. Maximum potential energy, zero kinetic energy. As it plummets, it converts that potential energy entirely into speed. By the time it hits the bottom, where the height is zero, all that stored energy is now pure motion, rocketing the passengers forward at a thrilling 28 meters per second. For context, that's roughly 100 kilometers per hour, just from dropping. Now, here is a fascinating quirk of this math. If you calculate the drop of a rock from, say, 3 meters up, its final speed of 6.3 meters per second relies purely on gravity, not on how heavy the rock is. If you look at the conservation of energy equation, mass is on both sides of the equal sign, which means it cancels out entirely. Whether you drop a tiny pebble or a massive boulder from a 3-meter ladder, they hit the ground at the exact same speed. All right, let's bring it all home with Section 5, Power and Energy Conservation. Up until now, we haven't talked much about time. That's where power comes in. Power is the measure of how quickly a force can get a specific amount of work done. You and a bodybuilder might both carry a heavy box up a flight of stairs. You both do the exact same amount of work because you moved the same mass over the same distance. But if the bodybuilder runs up the stairs in 5 seconds and it takes you a full minute, the bodybuilder has generated way more power. We measure this rate in watts. So, moving a heavy vehicle against gravity and friction at a steady speed demands a tremendous and constant rate of work. Consider a 1,400 kilogram car driving up a steep 10-degree hill at 80 kilometers per hour. The engine is constantly fighting gravity, pulling it backward, and friction dragging its tires. To maintain that steady speed, to do that massive amount of work every single second, the engine has to output nearly 68,000 watts. That's about 91 horsepower just to keep going. It's this perfect, real-world synthesis of force, velocity, and time. As we wrap up this explainer, I want to challenge you. Look at the everyday world through this lens. Try spotting the silent, beautiful math governing every single movement around you. Next time you hit the brakes or drop your keys or just walk up some stairs, remember the incredible interplay of vectors, forces, work, energy, and power that makes it all happen. You're not just moving through the world, you're living out the laws of physics. So, what invisible forces are acting on you right now, and how much power are you generating just by sitting there watching this? Thanks so much for joining me today. Keep questioning, keep learning, and I will see you next time.